This is Math 251, section 11.3. We're going to be looking at multiplying two vectors together, both in this section and also in the next one. There are two ways to multiply vectors. The first one is called the dot product, sometimes called the scalar product. The dot product of two vectors, as we're going to see, is called the scalar product because the answer to it will be a scalar, just a number. In the next section, we'll be looking at the cross product of two vectors. That's called a vector product because, again, as we'll see, the answer will be a vector. So we'll concentrate right now on the dot product. For starters, we're going to look at a motivation for the definition of the dot product based on the concept from physics of calculating work. Remember, work results when a force is exerted through a distance. And in basic non-calculus-based physics, you usually learn that work equals force times distance. Let's think about the assumptions that were really being made when we used that equation. As we can see, we were basically assuming, first of all, that the motion was all in a straight line. So straight line motion would be the first assumption. Secondly, we were assuming that the force was exerted in exactly the same direction as the object was moving. So force is in the direction of motion. And lastly, that the force was constant. This list of three assumptions, we will eventually be able to eliminate every single condition here, and we'll be able to find a very general way of calculating work. That is preview of coming attractions. For right now, we're going to keep the straight line motion and the constant force, and we're just going to talk about what happens if the force is in a different direction compared to the motion. So let's rephrase this in terms of vectors. In this specific situation, where the direction of motion and the direction of force are the same, what we see is that the force would actually be the magnitude of this force vector. So if that's the force vector, then F here becomes just the magnitude of F. And if the direction is identified through that vector, then the D becomes the magnitude of D. So in the case that all three of these conditions are satisfied, work would be the magnitude of the force multiplied by the magnitude of the distance. Now what happens if we allow for the force and the direction of motion to be different? So here's my force vector. And notice it's not in the same direction as the distance vector. Not all of this force counts as work. Only the part of the force that actually helps me move in this direction is going to count. So in fact, only the piece of this force that's really horizontal is going to help me out and count towards the work. Fortunately, we know how to get that, right? If I were to just sort of build a little triangle here, like we've often done for F1 and F2, then the horizontal part here would be the magnitude of F cos theta, and the vertical part would be the magnitude of F sine theta. Because only the horizontal part actually helps me move in the horizontal direction, this is the only part I can count in my calculation of work. So work becomes this piece of the force multiplied by the magnitude of the distance vector. Or we often pull those two magnitudes out in front, the magnitude of F times the magnitude of D times the cosine of theta, where theta is simply the angle between F and D. If you're concerned about my definition of theta being that angle, please keep in mind that in this diagram, these vectors are not in standard position, right? They don't both start from the same point. So you'd actually have to imagine taking this F vector and translating it so it starts at the same point as the D vector. And then you can see that the angle theta here really is the angle between them. It was just obscured by the fact that they weren't drawn in standard position. All right. Notice, by the way, that this is completely does not contradict this statement, because when F and D are in the same direction, the angle between them is 0, and the cosine of 0 is 1. So even if I did have a cosine theta on there, it would just be 1 in this case. So those two formulas do work really well together. All right, this actually provides a new way to sort of multiply two vectors together. I could consider this the product of the force vector with the distance vector. And we'll use that to define our dot product. We'll say the dot product of the force and the distance is magnitude F, magnitude D, cos theta. Or we can even generalize that and talk about a dot product for any two vectors, not just a force and a distance. So here's the general definition of the dot product, building on what we just did. If W and V are any two vectors, theta is the angle between them, then W dot product with V is magnitude W, magnitude V, cos theta. Notice that this dot product is a scalar, right? The magnitudes are scalars. The cosine of an angle is a scalar. This is just a scalar. And also that the dot product is commutative. U dot V is the same as V dot U. All that would happen if I changed the order here is that I would swap where the magnitude of W and the magnitude of V were. And of course that wouldn't make any difference to the final answer. All right, we'll need to do a little geometry and trig to use this definition of the dot product, but we're going to practice taking a few dot products. Here I've got a W and a V. Let's just start by drawing them. W is 3i plus 4j. So 3, 4. There's W. And V is just 7j. I've got to go up a little bit higher here. There's V. And my goal is to find W dot V. So magnitude W, magnitude V, cosine theta, where theta is going to be this angle between the two vectors. All right, well, the magnitudes aren't difficult. Magnitude of W is just going to be the square root of 3 squared plus 4 squared. And the magnitude of V, probably don't even need to write it out. It's pretty clear that the vector has length 7, but if we were to write it out, it would be the square root of 0 squared plus 7 squared. And then this cosine theta that we're going to have to talk about. All right, that's 25. Square root of 25 is 5. Square root of 49 is 7. No problem there. Now what about this cosine theta? I claim we can actually read the cosine of theta right off this picture. Let's go ahead and make a right triangle here that contains the angle theta. Clearly this side of the triangle is 4, and that side is 3. The hypotenuse is just the magnitude of W, which we've already calculated. It's 5. You can just use the Pythagorean theorem, right? So the cosine of theta is going to be adjacent over hypotenuse, or 4/5. My 5s will cancel out, and I'm just going to get 28. All right, let's try another one. This time W is 2, 0. And V is -1 square root 3. Square root 3 is around 1.7-ish, so I'll put it right there. There's V. So once again, to get the dot product, W dot V, I'd have the magnitude of W times the magnitude of V times the cosine of theta, where theta is this angle between them. That's going to be the square root of 2 squared plus 0 squared. Again, you can already tell the length of that vector is 2. Times the square root of negative 1 squared plus the square root of 3 squared times the cosine of theta. Square root of 4 is 2. 1 plus 3 is 4 again. Square root of 4 is 2. And once again, I can figure out the cosine of theta simply by using this diagram. If I were to drop a perpendicular here down to the x-axis and form a little triangle, we would think of this side as a negative 1, just to get our signs correct. This was the square root of 3, and the magnitude of v is the hypotenuse. The magnitude of v was 2. And so adjacent over hypotenuse, negative 1/2 is going to be the cosine of theta. And multiplying those together, I'm going to get negative 2. You'll notice that the value of a dot product can be either positive or negative. If we think back and interpret like the force and distance for work, it kind of makes sense. In this first example, if you interpreted, say, W as the force and V as the distance, this force vector is helping somewhat to move the object along the y-axis. And we got a positive result for our dot product, which would be interpreted as the work in that context. Here, however, if we interpret V as our force and W as the distance the object moves, notice that the force vector V isn't helping at all. In fact, it's taking away from our attempt to move here. So in this case, we get a negative value for the work. In other words, V is not doing any work. We'd have to put work into the system in order to get the object to move along the vector W. So that's sort of an interpretation of what we mean by a positive versus a negative dot product. All right, let's try a couple of three-dimensional examples. Here we've got a W and a V, and I'm really not going to make much of an attempt to draw them super accurately. I'm kind of going to wing it, to be honest with you. W is 1 in the X, 2 in the Y, 1 in the Z, so maybe around there. Now notice that V is exactly double W, boy that's hard to say, double the value of W. And so V is going to be the exact same direction, but twice as long. So there's V. Same direction, twice as long. That's great because now we know the value of theta, right? The vectors are in the same direction, so theta is going to just simply be 0 degrees. That's going to help us a lot. All right, definition of the dot product here. We'll do our magnitudes. And I'm going to fill in theta. Theta is 0 degrees. The angle between the vectors is 0. So I've got the square root of 6 times the square root of 16, 20, 24. Cosine of 0 is 1. And I think that's 144, isn't it? 6 times 24? Yeah, 6 times 24 is 144. Square root of that is 12. 12 times 1 is still 12. So there's a three-dimensional dot product, only doable because it was so obvious what the angle between the vectors was. Here's one more three-dimensional example. Again, it's going to be obvious what the angle is, otherwise we would not be able to do this. So W is 2I plus 3J, and V is 2K. So notice that W is in the XY plane. 2 on the X, 3 on the Y, be about there. V is 2K, so 2 units straight up the Z-axis. There's V. So the angle between these two vectors is going to have to be 90 degrees. Since the Z-axis is perpendicular to the XY plane, any vector on the Z-axis will be perpendicular to any vector in the XY plane. So theta here is 90 degrees. All right, let's go ahead and do our dot product. The magnitude of W times the magnitude of V times the cosine of 90 degrees. Let's see, 9 plus 4, that'd be the square root of 13. Square root of 4 is 2. And the cosine of 90 degrees is 0. So this dot product just turns out to be 0. In this last example, we said these vectors were perpendicular, and the way I have them drawn, they are. But in this class, we'll often use another word instead of perpendicular. We'll often call those vectors orthogonal. The reason for that goes back to the idea of the freedom of vectors. This vector, W, didn't necessarily have to start at the origin, right? I drew it in standard position, but it could have been anywhere out here, and it could have not exactly intersected with V, and yet that element of perpendicularity would still be there. And therefore, we use the word orthogonal to talk about, because of the freedom, vectors could maintain the basic relationship of perpendicularity, but not actually intersect. You might be able to see this here. If I imagine two vectors, I can put them even like this, that intersect at a right angle. If you just imagine taking one of those vectors and just lifting it straight up, notice that it's sort of like it's still perpendicular, but they don't actually meet anymore like they used to. So these are perpendicular and orthogonal. When they don't meet, I just call them orthogonal. I'm going to actually use this last idea to go ahead and generalize in a little theorem, the special cases of the dot product. We'll talk about it and then we'll fill it in. They talk about what happens in the parallel and orthogonal cases. In the parallel case, we end up with the magnitudes of the two vectors, and the cosine of 0 degrees is just going to be 1. So in fact, it doesn't really change the product. And what we really end up with is just the magnitudes of the two vectors. So I'm going to say U and V are parallel if and only if, and there's actually two pieces to this. Oops, let's make this W and V. I don't want to insinuate that it's a unit vector. W dot V is equal to the magnitude of W times the magnitude of V. This is the same direction case. The other possibility for parallel is that the vectors are in opposite directions. If I go back up to my picture for just a moment, had these vectors been in opposite directions, there would have been a 180-degree angle between them. And the cosine of 180 degrees is actually -1. So I would have gotten minus the product of the two magnitudes. So the other possibility here is that W dot V is minus the magnitude of W times the magnitude of V. And that's still parallel, but the opposite direction case. All right, the other one is the orthogonal. Orthogonal means that we do have the 90-degree angle, And since the cosine of 90 degrees is always 0, W and V will be orthogonal if and only if W dot V is 0. By the way, notice this if and only if is a really strong statement. It means that if I know they're orthogonal, then their dot product is 0. But also, if I know their dot product is 0, I can go back and conclude that the vectors were orthogonal. So we'll use that statement both ways, as you'll see in some of the upcoming examples in the next video.